Ursula is going to tell us about framed knot contact homology.
Okay, so in this case, this is actually the third paper on the subject I inked, and in this version of contact homology, our generated U is set equal to 1. And the mu might be set to mu inverse respective to what we had before, but again, we'll be working from that definition of knot contact homology, and I'm going to spend this half an hour mostly talking about how the degree 0 knot contact homology is isomorphic to the chord algebra of K, and hopefully further motivate the definition of knot contact homology, especially some of the things that I mentioned in the last 5 to 7 minutes of the other talk, because I wasn't very clear. And I was using this even though I hadn't defined it. So we're again going to start with the braid B. And the braid group, and we're going to be considering knots, well, a knot whose closure, which is a closure of B. Huh? And in this case, we're going to have that if we have two braids B and B prime with isotopic knot closures, then their respective DGAs are stable tame, isomorphic once we take lambda to lambda mu and for an integer n, which is measuring the difference in the rise of the two braids. So again, just to reiterate, we've set u equals 1. We may have changed a few of the mu's, but we've got a knot invariant here up to this change. And again, from last time, lambda and mu were giving us the framing of the knot K, because we could associate, where lambda is the longitude and mu is the meridian. Okay, so now I'm going to define the chord algebra, which is the object I really wanted to talk about. So it's just going to be, we take a knot K in S3, which is oriented with a point star on K. Then we're going to define a chord of K comma star to be a continuous path gamma from 0, 1 into S3 with endpoints on the knot that does not pass through the point star on the knot. So if I were to draw the end knot, a chord could be this guy. Let's say this is our point star, or it could also be here. If I had a more complicated, or like a trefoil, then maybe my chords could be passed like this, or like that, or like that. That's not a very good picture. Yeah.
So just to be clear, those don't pass through the knots.
They're passing
over. Yeah.
Yeah. But they end at the knot. So their endpoints are at the knot. And we're going to consider an algebra A generated over Z, measuring lambda equals 1, generated by these chords of K comma star. And we're going to mod out by skein relations, which I'm going to draw right here. So, do I have enough space? Yeah. let's say the arcs are going to be in red and the knots in black. So if this is a strand of the knot, if I've got a cord with endpoints on the knot that's contractible and that's not passing through the point star, then that can set that equal to 1 plus mu. If I have, this is again my knot, if I have a cord that's to the left of the star point, then I can move it to the right of the star point, but I have to add in a lambda factor. And similarly with the other directions. I can move it to the other side, but I have to add in lambda. And if I have a cord going over the strand of the knot, that's going to be equal to plus mu of the cord going underneath the knot, and that will be equal to the cord ending at this strand times cord. Can everyone still see? Or once I get out of the way, perhaps. So if I've got a cord that goes over the knot, then plus meridian times a cord going underneath the knot, that's the same as a cord ending at that strand or beginning at that strand.
And again, it's up to any kind of isotopy you can only think of, right?
Yeah.
So you can move the start and end points along the knot,
Yes.
but not through the
star point.
the base point.
Yeah, the base point. Yeah.
Can you move the ends to each other?
So you're
Yeah.
saying doing this?
Yeah.
Yeah.
That would give you a lambda factor.
Not unless it
No.
passes through the.
Both are equal to 1 plus mu, so there is no problem.
Yeah. So if I were to do, I think this is like that, that would also be 1 plus mu. Because, and I'm not passing through the base point. What we have to worry about is the base point. Okay.
And you can say that maybe we can see your drawing with
Yeah, so this one, if you look at it from behind, also holds. Yeah. There's another definition of the chord algebra which generalizes for codimension 2 connected submanifolds. I'm just going to write it because of time constraints for knots in R3, but it's going to help us generalize later on, and I think it ties into definitions from tomorrow on strings. So I'm going to write that really quickly. So you can have an equivalent definition where you start with a knot K in S3. You consider the tubular neighborhood of the knot, and you pick a point, tubular neighborhood, you pick a point x0 in the tubular neighborhood of, in the boundary of the tubular neighborhood of K. And we're going to have that this has an orientation. So we get an element in pi 1 of delta K x0 immediately. So just to sketch that out. Once I've picked a point here, x0, I'm getting an oriented loop. And we can map from the fundamental group down to h1 of delta vk. And we're going to set p of m is mu. And also if I've got a longitude in here, that's going to be lambda. So, yes. Now, our chord algebra, oh, I don't want to erase this. I'm going to move it right here, is going to be equal to 3 adjoint lambda plus minus 1, mu plus minus 1, generated over the elements of pi 1 of the complement of the knot based at x0. So we're looking at any element here that could also wrap around. But in this algebra, I'm going to have that, if I concatenate loops, for instance, that's not necessarily the same as this. So just as a word of warning. And we're also going to ask for the following, we're going to quotient out by the following subalgebra I in order to get the chord algebra. So we're going to set, this subalgebra is going to be generated by E minus 1 minus mu. Gamma m is equal to mu times gamma. Gamma L is equal to lambda gamma, and gamma 1, gamma 2 plus gamma 1 times m gamma 2 minus gamma 1 dot gamma 2 is equal to 0, where here gamma is in here as well as gamma 1, gamma 2 are up here. So now we're quotienting out by these elements, and when we do that, our chord algebra of K is going to be A mod I.
Sorry, just lagging behind a bit. So this is the free algebra generated by the set
Yeah,
of homotopy, by the set of
homotopy classes of loops
Okay,
in the complement based at x0.
yeah. So it's not the group algebra.
Yeah,
Okay.
and because of that we don't have this. Yeah. And then we're going to quotient out by this subalgebra. And in fact, these turn out to be equivalent definitions. I'm writing this one down because it generalizes to codimension to some manifolds in a general manifold M.
Maybe you can write the phrase chord algebra somewhere on the board, since you've now defined it twice without.
Chord algebra, and then this is A with scaling relations, so I guess modulo scaling relations is also the chord algebra. Yeah, so we have two equivalent definitions. And let me talk about why they're equivalent for a second.
Where did either of them come from? Like, why this scaling relation?
I am not sure.
Yeah, so what sort of answer do you want? So compared to the algebra that Ursula had this morning, there's some sort of fairly clear correspondence where the arcs from this morning then become chords here, and the homomorphism that gives you what you're modeling out by becomes this relation.
I want a geometric.
You want a geometric explanation? Yeah, we'll talk afterwards.
Is it just a base point? Something?
It's no, I mean, it's just a weird relation. There's something about, yeah, well, sorry, we'll discuss afterwards.
Or maybe in the end of the day.
Yeah.
Okay, so to be talked about later. But so how are these definitions equivalent? We're just essentially going to consider a chord is defined here, and then we can pick a point that's not the star point. And we can get a path from, say, a point x to x0, and perhaps to another endpoint, or just back here. And we can get the chord that starts and ends at the knot. And then we can go from these skein relations exactly to these. So for instance, if I'm doing nothing at x0, I'm going to get -1 minus mu, and we'll get a contractible chord. So a better picture perhaps is that what we're doing, where do I want to write this? I guess I'm going to erase this. What we're doing, we can also think of starting with our knot K, and we're finding a push-off, which is going to lie, let's say this is x0. And if before we had, say, chords that were coming out, or arcs, from the knot K, we were saying that perhaps these two would be the same when we had lambda and mu equal to 1, if you ever do that. But now, if we have the framing, and we want to take that into account, these two chords should be different, because one's clearly wrapping around while the other one's just coming out. And so if you look at, say, is that the picture I wanted? Yeah. If you look at this one, it's, sorry, let me think for a second. I had my drawing mixed up. I'm going to make a wrap around again to make the picture easier. If I have this loop, if I were to bring this over here, I would have a different loop where it's going behind here than if I were to shoot out straight and just have, say, a loop here, right? So by looking at chords that now start on the push-off, I'm actually picking up whether I'm going around a meridian or around a longitude. That's also, you're actually picking up how the chord's shooting off of the knot. Yeah.
So in what direction? In what direction do you push off?
You can, so once you've picked your point x0, you would just push off along that. It doesn't, I don't think it doesn't matter. Yeah, but I don't think it really matters.
This discussion has suppressed something which is that the isomorphism actually involves some additional powers of mu that come from some sort of framing. So,
Okay.
there's actually a
Yeah.
choice of how you push off, but it's independent of the choice because you correct it by this power of mu.
So, yeah. So that would be what happens. And then, in order to show that H0, the degree 0 contact homology is a chord algebra, we have to consider arcs. So now, if I want to talk about that, we want to do we are going to have K as the closure of a braid B, and which is sitting in a solid torus T. And Antoine mentioned this, but we're going to set our knot K to kind of lay close to the end knot, usually. And wait, sorry, that's a different statement. Anyway, so we've got our knot K, and we can push off K to get K prime. So you have the push off given a certain choice of framing. And you can arrange it so that at any slice, K and K prime intersect a disk D, kind of going along, in endpoints. So you'll have, this is the intersections given by K prime, and these are for K. Or basically by, if you like isotope the knot, you can get that at any slice. You just are seeing this, right? And then we want to homotope the chords so that they lie in the disk with these punctures. And we're now considering chords that start and end on K prime, push off. So perhaps like that. And I'm going to say this kind of quickly, but essentially, when you use that isomorphism that we had, going from arcs, now we're going to be doing frame arcs, to the algebra generated by the AIJ, you're going to find exactly the relations given by partial B, partial and partial C, and partial D, which are defined over there. Yeah. And this way, since you know that H0 is just generated by 0, okay, it's just the AIJ modulo delta B to C delta D, then you've got that it's just the chord algebra. So this is going through it kind of quickly, but yeah. This gives us a topological way of thinking about knot contact homology, and to my understanding there isn't one for degrees 1 or higher. So this is what we have. So compared to when we had mu and lambda equal to 1, we could not detect certain knots, but now if it's not equal, if we are considering knot contact homology with the framing, we can detect mirrors of knots, we can detect changes of framing, and we can detect inversions. And so in particular, if I were to start with a knot K with DGA, A comma delta, and I were to look at its mirror, let's say K tilde, then there is, we can take this DGA and just change mu to mu in 1 over mu. And then the DGA of its mirror is stably tame isomorphic to this DGA. And this is why we know that they're different. Or that
Well, this doesn't
this
prove that
knot
they're
contact
different.
homology,
This suggests that
giving-
they could be different, and in fact, you can check in examples.
that they are. Right, okay. How am I doing on time? Is it?
You have about 5 minutes.
Okay, so I might be able to. So for changes of framing instead, you would map the DGA from lambda to lambda mu f. And for inversions, you take lambda to 1 over lambda and mu to 1 over mu. Yeah,
So by inversion, you mean changing the orientation.
yeah.
Yeah, that's actually open, meaning we don't know that you can actually detect orientation reverse using this.
Okay,
But,
but
I mean,
you
what
find
read
that the
is correct,
DGA is...
That's right.
Okay, so I shouldn't say that, but I should say that the DGA of K, when mapping to the DGA of K prime, can be mapped from here to here by doing these changes. That's the more precise statement. And then maybe I was going to perhaps talk about the last part of the paper that's called the augmentation polynomial, but I don't know if it makes sense to do that in 5 minutes.
Can I ask a question?
Yeah.
What's the difference between this arc maps you have now and the version you have earlier today, like without the white dots?
Just that before they were starting and ending on just the knot, and now I have them starting and ending on the knot K prime. And if they wrap around, you have to add in meridian often. So you'll have more relations.
Do you have the same kind of the scaling relation as you draw when you cross a white dot? Like
Yeah.
you draw an arc that go under the a white dot, and then can you apply the scaling relation at that white dot?
Well, if you go underneath a white dot, you're just going to be adding in a mu. And then your scaling relation of going over or under will be for when you're on the push-off K prime, I believe. Yeah. Yeah.
And then when you apply the scaling relation at that white dot, you introduce the chord that end and start at that white dot. So use your arc algebra that contains more arcs.
But I think she
So
said
are you
that-
saying, can I do this?
The scalar, yeah, it's not enough. It's not
So the picture you had before was the correct picture, except that the question was, what if it keeps going, and so you have it just ending there, but it could keep the arc could keep going, right?
Yeah.
And then there's a scaling relation that involves that.
I'm sorry. Do you mean like
I really do not
going
want
up
to end it.
here and then like
Yeah.
perhaps over here?
Yeah.
There'll be a scaling relation if it is going over or under punctures in K prime.
Yeah. So this is the picture where it goes under, and then there's a corresponding one where it goes over.
So if we were to draw this out, then this is, did I write this down here? I don't know, let's get this guy. So for instance, if I were to do, actually, if I were to have this one, that is just going to be the same as me times this guy, right? And if I have a scaling relation where I'm doing this, then I would first deal with getting rid of it going underneath here, and then I would deal with how it's going underneath a puncture in K prime, I believe.
So you're not allowed to go between the pair of the white and black, I guess.
No, the arcs begin.
No, they begin and end on K prime.
No, but you're allowed to go between them. It's just you have to be in the complement of K. Always.
Are you saying begin on,
No, I said
K prime
that
and end on
you have
K.
an arc that's that the middle part of the arc allowed to go between a white and black.
Yes.
So perhaps something like this, but then it goes like that?
Maybe.
No, that's exactly what it can't do. So an arc is exactly a path that's in the complement of those points that she's labeling as K, and with endpoints on the points that she's labeling as K prime. But besides that, it's free to move around.
Okay. I think I'm now out of time. So I'm here. Yeah. Are there any questions?
Questions for us?
Is there any connection between these and crossless matchings? What's called crossless matching?
I don't
Not
know.
as far as I'm aware, but it's an interesting question.
okay, let's thank Ursula again.